Hello everyone, my name is Daniel Weber and I welcome you to this talk called Exploiting Augmented Reality for Extrinsic Robot Calibration and Eye-Based Human-Robot Collaboration, which is a joint work together with Enkelejda Kasneci and Andreas Zell. So what is the setting? As you can see on the image, we have a robot in front of a table with various objects on it. And we now want to point out objects to the robot, which the robot should detect and interact with, for instance, an object he should grasp. To point out the object of interest, we want to use the human gaze. Therefore, for the general interaction between human and robot, we use the HoloLens 2, which is a pair of augmented reality glasses from Microsoft with a built-in eye tracker. Before we can segment the objects of interest, we first have to solve two other problems. The first one is gaze mapping. So the HoloLens provides gaze as gaze vector and hit point with the environment in the coordinate system of the HoloLens. Now, a robotic system typically has many 3D coordinate frames that change over time, such as a camera frame, a gripper frame, or a head frame, and so on. For the robot to know at which object the human is looking at, we need the gaze information in a robot's frame of reference. This should be independent of the human's current view, so that he can move around freely. That means we have to know both the transformation in between HoloLens and robot, as well as the transformation between robot and the camera attached to it that points at the scene with the object. Thus, the second problem is extrinsic calibration of the camera. There are different ways to calibrate robot extrinsics. For example, through indirect co-location, using natural points in the environment or markers, or analytical methods or manual measuring. All have in common that they are often time-consuming or use expensive software or hardware. Also, if the sensor, in our case the camera, is moved, the calibration must be laboriously repeated. In this work, we tackle both of these problems together. The idea is to use the HoloLens as bridge between the coordinate frames. We create virtual counterparts corresponding to the real ones. That means we place a QR code at the robot's torso where the transformation to an existing robot frame is already known, and we do the same with a QR code at the camera. On this image you can see the view from the human through the HoloLens. On the right side we have the user interface, and on the left side you can see that the real camera is overlaid with the virtual model of the camera. Now this is the pipeline we are working with. The QR codes determine the pose of the virtual robot and the virtual camera. Since the pose of the virtual and real objects are the same, we can calculate the real transformations from the position and orientation of these virtual versions, which we know in the frame of the HoloLens. Finally, we can publish this transformation and also the gaze information via our user interface. So on the one hand, we can calibrate the position of the robot and the camera in relation to each other. And on the other hand, we can establish a direct transformation between HoloLens and the robot, which means that the robot is aware of the gaze point all the times, regardless of the field of view. In the bottom left is a visualization of where we are at the moment. We know the poses of the robot, camera, and human wearing the HoloLens, and we can track the gaze. Here, the green arrow is the gaze vector, and the intersection with the environment is the hit point. That means the point where the human is looking at. Now we are able to continue with the segmentation. We address this task by enhancing existing segmentation methods on the robot side with gaze information from the human collaborator. Thereby, everything should work continuously and in real time, and the assistance that the robot receives from the human should be limited solely to the provision of the gaze information. Apart from that, the segmentation should only take place on the robot side. This makes sense due to the high resources and computing power of the robot compared to head-mounted devices like the HoloLens. So the segmentation pipeline is as follows. As input, we use the point cloud obtained from the camera. In the second step, we apply a path-through filter and a voxel grid filter. This is not absolutely necessary, but it reduces the computing time significantly. In the next step, we transform the normal of the surface which the objects are located from world frame to the camera frame, which is possible due to the previous calibration. Afterwards, we use the normal to remove said planar surface using Ransack. In the last step, we find the closest point to the gaze point within the point cloud with a KD tree. This point, combined with Euclidean clustering, finally yields us the Jack cluster. Here we can see what the results look like. On the left side, we have some segmented objects where the human was looking at. On the right side, the view of the human through the HoloLens is shown. And as you can see, it is possible to give feedback to the human in form of an augmented 3D bounding box. Thus, the human knows immediately what object the robot thinks the human is looking at. In order to evaluate our calibration, we use OptiTrack, which is actually a motion capture system. For this, we attach multiple markers to the robot and its camera, in this case an Azure Kinect, that are tracked by the system. You can see an illustration in the image on the right. The precision of the tracked markers is below 1 mm, but post-processing increases this to 2 to 4 mm. In this way, we can get some kind of ground truth with which we want to compare our method to. We do this separately for the translation and the rotation. For both translation and rotation, we do the calibration in 3 different poses of the camera: vertical, horizontal, and tilted. For each of the poses, we do 20 calibrations and record the special distances. In the box plot on the left, the distribution of the individual Euclidean distances to the ground truth are shown. As you can see, the vast majority of values has a precision below 5 mm, and all the medians are within the range of the accuracy of the ground truth. On the right side, you can see the rotation error. In general, each rotation can be expressed by an axis of rotation and an angle of rotation. This rotation angle can be considered as a measurement of the similarity of 2 orientations. Here, except of a few outliers, all values are below 2.2 degrees and the medians are in the area of 1.9 degree and below. Overall, the calibration is therefore suitable for use in real-world scenarios, which we will also see later in the demo. In order to evaluate our segmentation method, we trained several neural networks on household items from the Sun RGBD dataset. Our experiments have shown that the results claimed in the respective papers are difficult to achieve in practical applications. One possible reason could be that due to comparability, the evaluations are usually conducted on the same few categories, with large objects like table and couch. As a result, performance on other classes is often significantly worse. In numbers, that means that the mean average precision of frustum convnet at an intersection of a union threshold of 0.25 was only about 28%, and for VoteNet it was even below 1%. As a consequence, a meaningful comparison was therefore not possible. So we came up with 2 alternative approaches. We first labeled the 3D bounding boxes in the data by ourselves. And to avoid vulnerability regarding bias in labeling, we also projected the points segmented by our method onto the 2D image plane and compared the resulting 2D bounding box with faster RCNN. Here you can see the segmentation results. In the table on the left, you can see the intersection of a union between the bounding boxes obtained by our method and the respective ground truth shown for 10 test objects. In 2D, all intersection of a union values are 0.78 or above, with a mean of 0.81. In the 3D case, the values are naturally a bit lower, but still in the area of 0.6 and above, with a mean intersection of a union of 0.69. If we take a look at the recoil curve as a function of the intersection of a union, we can see that both curves show a recoil of 1 at an intersection of a union threshold of 0.5. This is particularly impressive in the 3D case, as we recall that the threshold of 0.5 is twice the threshold typically used for 3D object detection, as well as in the previously mentioned papers. In general, an object is already considered to be detected at a 3D intersection of union of 0.25. Finally, I would like to show you a small demo of the system. For the calibration, we just have to select the 2 markers. The one at the robot's torso and the one at the camera sensor. It is fast, simple and very flexible, which makes it possible to change the tilt of the camera sensor even during runtime. After the connection is established, the human can move around freely and all gaze information is available to the robot in real time. Leveraging this gaze data, the robot is eventually able to segment the objects that the human is looking at. The robot also provides visual feedback to the human's augmented view in the form of a 3D bounding box. Thank you very much for your attention.